Hello and welcome to the last video of the year of 2023. And what we're going to be doing today, we are going to be writing some bare metal code, some low-level code for an STM32, and we are going to write ourselves a driver for a WS2812B LED RGB LED. Now, if you don't know what those are, let me show you here. So these are things that are commonly referred to as NeoPixels, which is kind of a brand name from Adafruit. This is just kind of a family of RGB LEDs, like addressable RGB LEDs, and the idea is that you can stick them in a matrix or on a line, and kind of individually control all of them. So control the brightness and the color of each of these individual kind of pixels, as Adafruit likes to call them. But if you search for WS2812, you will also find kind of more generic versions of these things. And so I actually have basically this exact little contraption here on my desk. I'm going to show you here because I think the focus is probably not great on it. But I've got kind of one of these things here. We'll leave it for now. We'll go back to the image. And yeah, what we're going to be doing is we're going to be writing a driver for this. And the idea is that we want to have a kind of high-level API in order to basically say, hey, I want the first one to be this exact shade of green, and I want the second one to be this exact shade of red, and I want the third one to be off, and I want the fourth one to be white, and so on, right? So we want to have a high-level API for that, and then we want to have a low-level API, which is actually going to talk to the hardware, and by the hardware I mean the individual little chips that are on each of these LEDs, and there is an actual little piece of silicon, a little chip on each of these LEDs, which kind of has some ability to do basic communication, and it does all of the actual control of the LEDs, right? So we're going to be writing a driver for that. And yeah, let's just dive right into it. So I've prepared a couple of drawings here, and I also have the datasheet open, but let's take a look at the drawings first. So this is basically like kind of what one of these WS2812 looks like in like a very schematic form. So it has 4 pins. It's got a power in, the VCC. It's got ground, so it's the the ground of the circuit. And we have something called data in and something called data out. So notice that there's not like kind of a red channel, a blue channel, and a green channel. There's a data channel, and there's some sort of data out channel, right? So this is what it is. It's a real simple circuit, and that's kind of the the beauty of this device, is that it's kind of so simple. It's really a sort of packaged up form of a kind of controllable RGB device, which makes it really appealing. So this is kind of how you wire them up and how you wire them up together. So on the top we've got our power, on the bottom we've got ground. So we give each of the individual pixels power and ground, and then we plug in a data control line into the first pixel. I'm going to keep calling them pixels. We can call them WS2812s or NeoPixels or pixels, whatever. RGB LEDs, all kind of interchangeable in this respect. And so we plug in data into the first, and then what we actually do is we wire this data out into the data in of the next. So we actually daisy chain these things together. And that's kind of, well, that's also a pretty appealing idea, is that just to add one more of these LEDs to your circuit or to your device, you can daisy chain it into the previous one. So it's really pretty straightforward to use. I should note that if you get like one of these devices, like what I have here on the desk, where it's kind of like, this is really, I think, an experimentation device, or you can sort of use these to make your own matrices. But if you use this, and especially if you use it with like the power supply that's going to a microcontroller, or you're trying to signal things with like 3.3 volts, which technically is slightly out of spec for these things, well, you might actually want to add like a capacitor to the back. I don't know if you can see this. I've put like a 450 microfarad capacitor on the back between the power lines, just to make sure that, you know, its power supply is nice and constant, because that can be a little bit of a problem. That's just if you're following along with this and you want to try the same thing at home and you're having some trouble, you're finding that it's a bit glitchy, you might want to try putting the capacitor on. Okay, so back to the schematic. This is our device, and when I say we're going to write a driver today, what I mean is that we're going to write a piece of code that from the microcontroller will somehow generate the right kind of signal to plug into this data in order for us to control it. So I think it's pretty interesting and useful for people to define what a device driver is, because it's quite an overloaded term in some respects, and it's applied all the way from things like Linux, you know, like full desktop Linux, to embedded Linux, to things on a microcontroller. So I think it's worth actually mentioning what, and of course other operating systems. I come from a very Linux-centric way of thinking, but so it goes all the way from, you know, high-level operating systems down to low-level microcontroller type code. What is it actually? What is a driver? Well, the idea of a driver is that you have a whole nother device, right? There is another device that you're controlling, and that device actually exposes some kind of electrical type interface to you. So in that respect, that's like our data in, data out type thing here. And you sort of have to generate the right kind of electrical signal in order to communicate with the device, right? The device is a whole thing on its own, right? It's got its own whole world. It's a black box in some respects, but it gives us this interface. We have to somehow drive that interface, and that's why we call it a device driver. And I think it's pretty good to keep that in mind, because I think a lot of people, when they hear the word driver, they think, oh, this means something in operating systems. And of course it does, because a computer has all kinds of other sort of black box devices inside it, and it needs to communicate with them. So that's everything from the most obvious stuff like your graphics card. Obviously your graphics card is like a PCIe Express type device. It has a driver. There's all kinds of stuff that happens there. USB devices, they also have drivers because they also have specific ways of communicating, but that communication actually happens at, you know, different levels of the USB stack. And of course you also have inside even a modern high level computer, you'll have things like I2C devices or SM bus devices. So these are, you know, little embedded devices that speak over really simple serial embedded protocols. And all of these things need drivers. And so all of that stuff gets bracketed under the idea of a driver. All right, with that out of the way, let's move on to the next part, which is, what is the signal, right? What do we need to shove into this data inline in order to tell it to do what we want it to do? And I've got another little diagram here for that. So what we need to do is to shove in essentially color data to this thing, and we somehow need to shove in color data for every LED that we have in the kind of daisy chain system. And so how do we do this? Well, what we do is we shove in the green data first, and we have 8 bits for the green data for each pixel. We have 8 bits for the red data and 8 bits for the blue data. Notice that this isn't the traditional RGB arrangement, but instead this is GRB. And I'm not quite sure why that convention was chosen, or if there is even a reason to it, but it is the way it is. On this specific device, the WS2812B, this is the order of the color data. And just as a note, like, there are different kinds of these kind of pixel type devices, right? You have the WS2812B, you have just the original WS2812, you have the WS2811, and there are a whole other range of possible devices. They all speak a very similar protocol, so to speak. But there are some subtle differences in there, and one of the differences can be that the arrangement of these colors is different. But it can also be that the lower level part of the communication is also a little bit different. But most of it remains the same, and you'll be able to use this as at least as a reference point for that. So what do we need to do? We need to like send 8 bits for green, 8 bits for red, 8 bits for blue. So would you imagine that maybe you just, if you want to send bits for the green, like you would just have a 0 volt, a kind of ground level voltage when you have a 0, and maybe like a 5 volt or a 3.3 volt level when you have a 1. And you might imagine that's pretty common, but that's not the way it's done. And in fact, this protocol uses like a kind of non-return to 0 type encoding. It's an encoded form of putting 1 and 0, and it's also something called a self-clocking signal, basically. So this is how we would encode a 0 in this system. What we do is we bring the line high for 400 nanoseconds, and then we drop the line low for 800 nanoseconds. So that's, if we see that happening on the electrical signal, or rather if the device sees that happening on the electrical signal, it says, oh, I'm being sent a 0, right? That's how it understands that. For a 1, we kind of switch it around, and we bring the line high for around 850 nanoseconds, and then we drop it low for about 450 nanoseconds, right? So we kind of switch those two things around. So there's a couple of observations to make here. One is this is approximately like 25%. You could think of this being approximately a 25% duty cycle that we're sending. So if you imagine that we're sending a PWM, if you know what that is. If some of this stuff doesn't make sense, I really advise you go and watch my bare metal programming series, where I have like 18 videos that go all the way from not knowing anything about how an STM32 works to writing a bootloader and all of that kind of stuff. So if some of this stuff doesn't make sense, you might want to take a little look there. But yes, so this is kind of like a 25% duty cycle PWM, and this is kind of like a 75% duty cycle PWM signal, right? So that's one way we could already think about it, and that's one way you might think of starting to approach how we would write this as a driver. Like, okay, well maybe we can use a timer peripheral to generate PWM, and we'll switch up the timing on when we need to send a new bit. That's one possible approach. Now there's another thing to think here, which is if you're the other device, right? And I talked about this being a self-clocking signal. Well, there's one thing is that we can sort of understand how long we need to watch these signals for, but also the fact that the line goes high and then goes low, and we do have to do some counting because, you know, it goes low for 800 nanoseconds here, and we need to count how long it was high for. But the fact that it goes, it makes this transition, and the transition is what tells us that there is data on the line, and the length of that transition tells us something about what the data is. But there is a transition on the line, and we can use that, or rather the pixel can use that to, like, basically in a very simple edge detection type circuit to basically say, oh, there's data coming in. So this is the third observation, and I haven't said this yet, but I think it's worth mentioning, is that, you know, if you add this up, you get about 1200 nanoseconds. But the spec, and we're going to look at the spec in a minute, the spec mentions that it's plus or minus 300 nanoseconds, which is actually quite a wide margin if you think about it. Like, that's like a quarter of the time almost. So yeah, actually this is more like a third, of course. That tripped me up now, looking at that and thinking that's a quarter of the time. This is a third of the time. Okay, so that's about a quarter of the time. That's like quite a wide margin. So you can imagine that, like, I don't know, maybe that this is 150 nanoseconds longer or shorter, and the same thing here. So that's quite a, you know, that tells you something, that it's not just about the amount of time we need to count. There's something more going on here, and the device is actually quite forgiving in how you send this signal. That's going to be really helpful for us. Alright, so that is kind of everything you need to know about the signaling part. We could actually just go and write the driver now. But I want to show you the datasheet really quickly, just so you know where this information came from. So this is the datasheet. So this is a device, the WS2812B. It's from World Semi, that's where the WS part comes from. And I don't know why it's called a 2812B. This is not the first device in this series. If you've never really read a datasheet before, this one is a great one to sort of start with because it's just a few pages. It starts out with the classic kind of features and benefits and like kind of high level overview of the system. So it talks about some of the cool points that you might want to think about for this. So like, for example, each device has 256 levels of brightness, and you can kind of think of that as being the 16 million plus color spectrum. They have a cascading signal, so that's the idea of the data in, data out. Any 2 points. The English in this document is not the best. You have to be ready to kind of do like on the fly sort of English Chinese translation here, but any 2 point of the distance more than 5 meter transmission signal without any increased circuit. What they're telling us there is that we can run the transmission line, the data line, 5 meters without having any signal compromise. That is because the device itself does signal conditioning, right? It's able to take maybe a noisy signal that we've sent and like turn it back into a nice one. I think that there could be some problems with a 5 meter wire in other circumstances, but yeah, okay, maybe in very good conditions that can work. And yeah, you can get about a 30 frame per second cascade when you have 1024 pixels. Like when you're controlling 1000 of these lights, you can update them at 30 frames per second if you're driving the circuit optimally, and we can calculate that out in a minute, and we'll see that that is true. Okay, so then as you scroll down, you get down to more of the kind of like physical, mechanical kind of specifications. So like if you're laying out a board and you have to design a footprint, like this information is pretty important for you. Here we see information about the pins, so we've already seen this. They give them slightly different names, like VSS, that just means ground. Data in, data out. We can see the power ratings. All this stuff is important if you're designing hardware. Eventually, we get down to this part, which is the data transfer time, and this is where actually we get into the signaling part. I'm sorry, and I was just thinking there that I have an error in my thing because I said plus minus 300 nanoseconds, and they put plus minus 600 nanoseconds here, but I'm trying to think that doesn't really work out. That doesn't actually really work out in this if you think about it, because this would be minus 150 nanoseconds, this is plus. That's kind of your worst point. That's a 300 nanosecond span, so I don't know where this number 600 nanoseconds comes from, but okay, keep it in mind. So this is basically just telling us that when we're transferring a 0, the time that it has to be high for is 0.4 microseconds, which is 400 nanoseconds, and the time that if it's a 0 and the time that it is low for is approximately 0.85 microseconds. And that's another mistake I now know that I have in my drawing, is that this should actually be 0.85 and not 0.8. So when you kind of add all of these things up, you get a total time of 1.25 microseconds for both of them, which makes sense. And yeah, that kind of gives you that information. So this is where it came from. You can see that I've made a little bit of a transcription error there, but given the tolerances that we have, that transcription error doesn't actually make a difference. But it's good to know the actual exact numbers. Here you can see more of a schematic representation of that same diagram that I have. And then finally, we have actually to mention the fact that we have something called the reset code. So they call it the reset code here. Here they call it the ret code. They seem to make naming choices across this. And basically what this is if we go back to the drawing for a second here, we can see that we send these ones and these zeros for each of the bits of the colors. So what we're going to do eventually is we're going to send red, green, and blue, all 24 bits of that, all at once, for one pixel. But then, of course, for the next pixel, all we do is send the next set of data. And that's kind of the cool part about the daisy chaining. It's sort of like a shift register. The first pixel, if you send in the data, it will take that, it will say, this is my data. And then the next time you send it data, it will go, oh, this is actually for the next one, so I'm going to send it along. And it will just pass the signal to the next pixel. And of course, when you start sending it data for the third one, it will say, oh, so this one's not for me. It will pass it on. The second one will say, oh, this is not for me. It will pass it on. And that's how you cascade the signal downstream. So we just send all of the pixels data. And the interesting thing here is that they don't immediately change their, like, update their new value, right? They don't immediately take on the value that you sent to them. Instead, we need to send the reset code, the reset signal first. And that is basically just dropping the line down low for 50 microseconds or more. So we've been mentioning nanoseconds up until now. That's what I've found it easier to normalize all of these into nanoseconds. 50 microseconds is quite a long time, right, in nanoseconds, like 50,000 nanoseconds. So yeah, you actually then, you do all of the signaling and then you just bring the line down low for a relatively long time. And that's it. That is how this thing works. So once you send the reset code, all of those pixels, all the ones that you sent data to, they'll take on their new values. Alright, we've talked about this for a long time now. Let's actually get in there and write the driver. This is the drawing, and we'll save it. What I have here is a basic project that uses libopencm3, which is what I used in the bare metal programming series. It's a very thin, low-level kind of hardware abstraction layer over the cortex-m4 and m3 chips. So it's an open source library that aims to support sort of writing basic C code for a whole range of cortex-m chips. And of course, we have here an STM32 chip. It's the STM32F401RE chip, which is a fancy way of saying it's a Cortex-M4 chip that's got a certain set of features, and this is supported by that. So we are just going to be writing into this project. It's the same kind of basic project that I have in the bare metal series. So this is just stripped down to its very core. Alright, if you want to see how to kind of set that up and the things you need to get ready for that, you can look at the bare metal programming series. Yeah, alright, I think we're ready to start up here. So the first thing I want to do is I just want to take the chip and start trying to generate like some of the timings that are involved in that signal, right? So I want to be able to bring a line high and hold it high for like 400 nanoseconds. Like, that's my aim now. So if we just we go back to the browser for a second, and I'm not in the browser, I should be in the browser over here. If we go to the browser and we search up STM32, rather Nucleo was the F401RE pinout, and we search for the images, and we go to this first one, we can see here that well, there's a whole bunch of pins that we could choose from, but I'm going to just want to make sure that you can see this and I'm not blocking it out. I'm going to arbitrarily choose PC8 as the GPIO I'm going to use to send out this data signal. There's no particular reason for that. I'm just going to arbitrarily choose it now. And now is a good time to mention as well that the way in which we're going to generate this signal is through a technique called bit banging. Now, bit banging, if you've never heard of it before, all it means is that we're going to generate the signal by writing code using the CPU, basically. We're going to use the CPU to generate the signal. Now, this is not like always what you want to do. Often you want to try and delegate some of this responsibility to peripherals, because that means that you can use the CPU for other things, right? You can be running other code on the CPU while a peripheral takes care of generating a signal for you. So we previously mentioned the idea of PWM. That would be one approach. But in this one, I just want to talk about a generic way of doing it, which is to use bit banging, because basically every microcontroller in the world can do bit banging. And I think it's a pretty instructive way of learning about how to generate signals. So you may want to think about doing this a smarter way if you have another embedded device and you need to use the CPU for like your core application, and it's like, you know, although the CPU doesn't actually have to spend much time generating these signals, if you don't have kind of the budget for that, then you might want to try and figure out a smarter way of doing this using peripherals, using things like timers, PWM, and DMA. But we're going to use bit banging because it's just kind of more fun, more applicable to other microcontrollers. So if you're watching this and you're thinking, well, I've got an AVR chip or I've got some other kind of chip, you can probably just adjust this, like what we're going to do, to your own situation. Okay, with that out of the way, let's see if we can start bit banging this signal. So I'll just make a define here for now, which will be our this will be the, let's call it the LED port, and the LED port is going to be GPIO C, right? Because we said this was going to be on PC8, and then the LED pin is going to be GPIO 8, right? So we've got a LED port and a LED pin. Let's make a function here. We'll call it GPIO setup. And what we're going to do inside this function is just initialize the GPIO pin as an output, right? It's the only thing we need to do. You can do this with registers. I'm going to call the libcm3 functions, libopencm3 functions. They basically just write to registers, but this will make it even more generic and will make it even more applicable to anyone else. First thing we need to do is to enable the clock to the GPIO peripheral. So let's do RCC peripheral clock enable. And this is going to be RCC GPIO C, and the that's it. We just need to enable to GPIO C, and then we need to say GPIO mode setup, and we're going to set up the GPIO port. Well, that's going to be the LED port. The mode is going to be GPIO mode output, and then we're going to have GPIO pull up, pull down, none. We're not going to use a pull up on this line. And then finally, the pin is the LED pin. There's one more piece of configuration that I want to apply here, and that is to set up like the speed. So we can set the output options of this GPIO. So again, this is going to be the LED port, and the output type, so GPIO output, the O type is push-pull. Right, this is just to do with how the GPIO is actually wired up. Is it a push-pull pin or is it an open drain pin? And I'm not going to go into the difference here because it's not that important, but it's a push-pull pin in this case. Now finally, this is what I actually want to configure, is the speed. So here we can actually talk about how quickly this GPIO pin should like transition its signals. And it's kind of a funny thing. You might think, oh, I want to make it transition as fast as possible. But for various reasons, that's actually not what you want to do. You don't want to make it go as fast as possible, often, especially when you're making a production device, because that will cause you to throw out all kinds of electromagnetic radiation, because you are forcing a very sharp edge, which means it has a lot of high frequency components in there. So it's actually not something you want to do by default. We're going to set it to 2 megahertz here, and I'm going to adjust that if we need to, because I'm not sure if that is going to work out. I also need to say that this is for the LED pin here. Yeah, but basically what I want to make sure is that we're able to transition the signal at the right speed. If you don't transition fast enough, then your signal will come out distorted. Basically, you won't be able to make the right timings, and if you go too fast, well, you get really sharp edges, but you'll spit out electromagnetic radiation everywhere. All right, so I think we've configured the GPIOs. That's called GPIO setup here. And then what we're going to do is to just like, I guess for now, what we'll do is we'll just toggle the GPIO on and off, and we'll see how quickly we can actually do that. How quickly can we make the pin go high and low? So I'm going to have a variable here, UN16T pin value. We'll start it at 0. And what we'll do in this infinite loop here is we will call GPIO port write. We're going to write to the LED port, and the value we're going to write is the pin value. And then we're going to say that the pin value is going to be XORed with the LED pin. And this statement will have the effect of flipping the bit that represents the LED pin. And if we look at what the LED pin is, it's actually the 8th bit being set to a 1. So we're going to flip that value every time we call this statement, and it will go, basically this value will go from being 0 to LED pin to 0 to LED pin to 0. So we're toggling the pin on and off. This is probably in C code the fastest way we can do this, so I think that's probably a good start. How are we actually going to check if this works? Well, first let's compile the code. I'm going to run make. That seemed to work, so I think that's a positive sign. How are we actually going to observe this? How are we going to look at the timing? Well, the way I'm going to do it is I'm going to use my logic analyzer. So here I have a Salier Logic 8. I'm going to use this to measure the signal. But of course there are many ways to do this. If you have a scope, you can measure it with a scope. If you have one of the cheaper logic analyzers that you can get for like 10 euros on Amazon and eBay and AliExpress and all of those kind of sites, that will work fine for this as well. I happen to have the Salier, so I'm going to use the Salier, but you can use a much cheaper device to do this too. I need to mention that because every time I pull the Salier out, everyone's like, well, you've got this expensive equipment and you can only, well, no, you can do it with cheaper equipment as well, I promise you. Okay, so let's find a ground. There is a ground over here. This is real riveting stuff, is watching someone not actually be able to see someone plugging in wires into a device. Okay, so I've plugged in the wires. I'm going to run the firmware by running debug here. That's going to flash the device. You can see it put a breakpoint here on the first line, so I'm just going to let it run. And then I'm going to switch over to logic, where we can start having a look at the signal. So I'm going to press play here. And we can see that this whole thing is white, but if we zoom in, then we can see that we've got a square wave. And what we have is a square wave that's around 120 nanoseconds wide, and then it's around 140 nanoseconds low. So I'm not quite sure why there is a big difference between the low and the high there. It's probably some intrinsic hardware thing where it's switching. I don't exactly know, so I'm not going to speculate, but what do we see is we get approximately 120 nanoseconds high time and approximately 140 nanoseconds low. So it seems to be pretty consistent if I look at this. Yeah, looks fairly consistent. Sometimes you can see that it's 140 nanoseconds, so we're like plus minus, or not plus minus, we're like potentially plus 20 nanoseconds sometimes. Yeah, we have a spread of like 20 nanoseconds here. So, okay, I see more 140s in this area at least, and if I zoom in over here, this is 120, 120. Okay, so it sort of depends on where we are. But okay, that's a good thing to note. Let's go back to the code. So we've got 120 nanoseconds of being in the high state, and what we want to do is to try and get that to around 400 nanoseconds, right? So how can we do that? Well, there are many different ways we could do it, but the way I'm going to do it is to just insert some no-op instructions, and we're going to basically pad the code with no-ops, or maybe a loop with some no-ops in it, and try and use that to get us to like the right number of no-ops. So you might be thinking, well, wait, couldn't we use something like systicks? Like we could use the systic interrupt and we could count up nanoseconds and we could use that. We could do that, except using the systic to count nanoseconds is going to be like absolutely thrashing the CPU, because we are going to be constantly interrupting the CPU, like on a no, like I'm not even sure if we could get to that resolution, but even if that was an option for us, it's just way too many interrupts coming into the CPU, stopping it from doing other things. We would never be able to accomplish kind of like, you know, steady code anywhere else. So that's just like the systic is much more on a millisecond type resolution, and we're talking about nanoseconds, which is many orders of magnitude smaller than that. Okay, so what we're going to do is we're going to insert no-op instructions instead. So what I'm going to do is just use ASM volatile, so tell it to insert some assembly, tell it not to remove it by putting the volatile in there. And so let's just put one no-op instruction in, and let's see where we get from that. So we've got a no-op in there. We're going to run the code, go back to logic, measure the timing, and let's have a look. So 140, 140, 140. So it seems to be more consistently 140 now, if I look at that. So maybe we have gotten ourselves, well, let's zoom in on a different area first. Yeah, it looks fairly consistently 140. Let's add in another no-op and see what that does. So let's just, for now, just put two no-op instructions in. And switch back to, run the code, switch back to logic, run it again, stop. Alright, now we got 160. So now we're definitely, well, and now we got 160, and on the low end we have 140. So it looks like two no-op instructions gives us 20 nanoseconds of play. So let's go back to the code. So 2 times no-op is 20 nanoseconds. So to get ourselves up to around 400 nanoseconds, we might want to have, like, say 10 would get us to plus 200, and then we need another what would that be, 4 to get us to 80. So we need like 14 no-ops. So let's try and put 14 no-ops in and see if that gives us like around the right ballpark. I'm just going to put these on one line because I think that will just make life easier. So that's 2, 4, 8. That would be 16, and then let's take away 2 of them. Okay. Let's take a look here. Run that. Go back to logic. Oh, these are wider. Alright, we've got 280 nanoseconds. We're not there yet. 300 nanoseconds. So we can't rely on the linear idea of adding these knobs. It's going to be a little bit more advanced. We got to like 300. So I'm just going to double the number here, and we'll slowly remove them until we get to the right amount. So let's play that. And let's record in logic. What have we got here? 440 nanoseconds, 440, 460. Okay, so let's remove, let's kind of keep ourselves around 420 nanoseconds, because that's going to be like pretty in spec for both of the signals, like a 1 and a 0. So let's aim for 420 as the average, which means let's just remove 2 no-ops if our counting is to be believed. Let's remove 2 of these. Try this one more time and see if we average out at about 420 nanoseconds. Alright. 440, 420, 440, 420, 440, 420. Yeah, like we're like splitting the difference on this. It seems that we're alternating on this. So I guess it depends on like how many instructions we run and kind of what's going on and when the switching occurs, but that's okay. I think we're within the range of I think we're within a range here. I wonder what would happen if we removed just one no-op from this. Like if I took out a single no-op, would that push us more towards the 420? Because we seem to have a relatively 50-50 ratio. You can see that this is very trial and error, and of course that means that there are Oh yeah, that's more consistently 420. So let's take that. Every now and again we get a 400, but it's way more often that we're on 420. Yeah, great. Awesome. And of course, like this is gonna work out nicely. All right, so of course there's a trade-off here. The fact that we are like just inserting no-op instructions means that we're very dependent on the speed of the CPU, right? So if this CPU happens to be running at 84 megahertz, if we were running at 72 megahertz, this number of no-ops is no longer going to work because it's going to be dependent on the number of clock cycles. So you have to think about, does this make sense in my application? Does it make sense for me to write this kind of driver if I know that this code needs to be working on some unknown clock frequency? Probably not. In that case, you need to start thinking about a different solution. You can still do something like this and still have bit banging, but you're going to need to like have the user like, and I imagine this would be in a situation like a library. You would need to have the user define their clock frequency for you. And you would need to have like, you know, if-defs basically to have different number of no-ops sort of placed in. So yeah, all right. So this is pretty good. So if we think about it, these no-ops, if I put these all on one line, this is this number of no-ops. I'm just going to put a define up here. This is no-op 400 nanoseconds. And let's put that on the same line. So we can actually just replace this. This is a horrible little piece of C here, but like this is basically 400, and maybe I should actually just put an X in here and not take anything and just, can we do that? So this is basically, will this compile? I just want to check that this does compile. I don't normally do like preprocessor crimes like this all the time. I think it's going to work. Yeah, it seems fine. So it's actually not 400 nanoseconds, it's 420 nanoseconds. And what I'm thinking here is like, can we just make the idea of 800 nanoseconds now? Because that's kind of the next part. So presumably, if we just did two of these in a row, we would get to approximately 800 nanoseconds. I think we're going to be over the mark, but let's have a look. Let's see where we get with that. Going to run this chunkier. Actually, we're on 700 nanoseconds. So yeah, it's not quite linear. This whole thing doesn't linearly scale, and that makes sense, right? It would be pretty convenient, let's say, for our random clock frequency, random to some degree, to like perfectly line up with like increments of 10 nanoseconds or 20 nanoseconds or something. That's not actually how it's going to work, and the Salier is not going to have a perfect resolution to get down to the nanosecond scale on these kind of signals, because the signals do have transitions in them. It would be good to look at how those transitions look, so like how it looks when we're transitioning this quickly, but I'm going to avoid that for now. So what I actually want to do is I think I'm just going to go back to having like not using this define. I don't think it's really helping us too much. So that's going to be our 420 nanosecond. I'm just going to comment it out, and we're going to figure out the 800 nanosecond now. So that's that. If we add another one of those on, and then let's add a little bit more on. Let's leave this many in, I guess. And let's see how close that gets us. Alright, we're running, we switch back to logic, we run 820 nanoseconds, 820, 800. This is perfect, alright? We're going with that. So that gives us this number of no-ops for an 800 nanosecond or an 820, and this gives us 420. I'm really happy with that. So that means that we can now generate the right like timing, right? The right number of like on-off time in order to start thinking about generating an actual 1 or a 0. So let's add another function here. This one will be called send0. And if we go back to the drawing for a second, we can see my slightly wrong but still accurate enough timing diagram. And so for a 0 is 400 nanoseconds on, 800 off. Okay, so 400 nanoseconds on, 800 off for a 0. So that means we would have this one first. And first we would turn on the pin. And actually in this case it's just going to be the LED pin. 120 nanoseconds. And this is going to be plus, what is it? I guess it's plus 300 nanoseconds, right? In this case, plus 300 nanoseconds. Then we're going to turn the pin off. We'll go to a 0. So that's also going to take 120 nanoseconds. All of this needs to be unindented by 1, which is also 120 nanoseconds, and then we'll have our 800 nanosecond kind of timeout here, and that means this is plus, what's that going to be, 780 nanoseconds. Alright, so this should be sending a 0. So let's actually just call this function now. Actually, what I want to do is I want to make it static inline, because I don't want to add, I mean, I know it seems stupid because we're going to have calls here, but I don't want to add like unnecessary timing, like uncertainty into this by having a function call on the stack. I just want it to like dump this whole function into wherever it's called. So send a 0, let's get rid of these. And we're just going to send zeros over and over again. And we're going to see if like the signal looks about right. And then we can make adjustments if we need to. So I'm going to let that run. Let's go back to logic. Let's do that here. And then what have we got? 380 nanoseconds. That's interesting. And about 800 nanoseconds off. So that's good. I'm going to add in another couple of NOPs there to make sure this comes up to about 400 nanoseconds. Just going to add in 2 more. I added in an extra one of those. Run it. Come back to here, run this again. Alright, 400 nanoseconds, 780. So like, this one's 420, this is 780. I'm actually going to add in 2 more to the 800 as well, because it looks like that is on the low end as well, and I'd rather it was kind of on the more on the high end. It's very trial and error, this whole thing. It's really about like trying to observe the perfect amount of timing. 400, 820, 400, 820. You can see that what we're getting on the spread here, like on this, you can see on this bottom timing here, you can't, I'm trying to point at the screen, you can't see that, but we got 1.22 microseconds, and that's really close to our 1.25 microseconds, right? So this is looking good. I think this is actually working fine. Let's now just invert this basically and write the code for a sending a 1. So sending a 1. So basically we just want to do this part first, and then this part is happening afterwards when we send a 1. So let's send a 0 and then send a 1. Okay, go back to logic, run. Let's take a look. All right, so in this case we get 780 and then 420, 420, 780, 800, 400, 400, 780. This is looking way within spec. So now we actually have the ability to send individual 1s and 0s. I think we can actually connect up the LED board and try and write out like a first instruction, like basically say, hey, I want you to be green or something. So let's try this. I'm going to create a new variable here, which is just going to be called start time. And we're basically going to piggyback on the timer now to create this like reset code that we need to have. So this is just going to be system get ticks, and we are going to if system.get ticks, which is like the current time minus the start time, is greater than or equal to 1000, like as in has it been 1 second? This is counting milliseconds. If it's been 1 second, then we're going to for I is less than 8 for 8 bits, I plus, we're going to send 8 ones in a row here. That's going to be sending the green channel. Green equals 255. And then what we're actually going to do is not send any other data. So we're not going to send the red channel or the blue channel, because you actually don't need to. You only need to send the data that you're interested in. It's quite a flexible protocol. I guess we could just send zeros for everything else. Maybe we should do that, just to make it like really clear what's going on. So this is going to be r equals 0, and then for this we'll send 0. Yeah, let's do it properly. And then this is going to be blue equals 0 as well. And then finally we will set our start time equal to this. And what that's going to have the effect of doing is making sure that we then spend 1 second not sending anything. And of course you need to remember that every time we send anything, we bring the line low at the end, right? That is the encoding. The line always goes back to 0, even if we're sending a 1 or a 0. So that will keep the line low for at least 50 microseconds. We'll keep it low for a lot longer than that, but at least 50 microseconds is what we need. So I'm going to just make sure this compiles. So we'll run that. It seems to. And what I'm going to do now is I'm going to plug in, I'm going to replace the logic analyzer, unplug that. I'm going to replace it with the WS2812 board that I have. So I'm plugging in the signal line, I'm plugging in the communication line up here, and I'm going to let it run. And yep, what do you know? I can actually see here, if I lift up the board for you, we have one green LED lit. So we've got a nice green LED showing. Let's change this up a little bit so we actually send a red instead. Let's send red and just make sure that this wasn't a fluke, or this isn't some sort of like unknown condition that's caused this to happen. Alright. Actually, there is something weird going on here. Oh no, this is correct. So I see that there's now yellow. It's a bit hard to see with the lights on here. I'll turn the lights off in a second. It's a bit hard to see. I've got yellow, but actually I'm still sending green here. So if we turn that off, and then we just send red, yes, now we have a red LED. So that's brilliant. So now we're actually sending data. We know the signal is working. We're able to control the device. What I now want to do is to take this like horrible timing code that we have and put it away into a separate file with a separate interface, and that will be our driver. So let's make up a, first of all, I'm going to make up a WS2812B.h file. So this is going to be the header file. This is going to be our common code, right? And first things first, just because I'm going to build a high level API here, you can do this in different ways. I realized I'm not showing the code, so I'm going to go back to the code. Type def struct RGB T, so I'm going to make an RGB struct, and I'm going to have UNAT R and G and B. And let's also include standard int, so we can use uint8. Alright, good. So we've got an RGB thing, so we can keep track of RGB LEDs. Also, I'm going to make another type def, which is going to be WS2812B That actually needs to go down here as well, and that needs to go down here as well. And what we're going to do here is we are going to keep track of like the whole object that represents this. So that's going to be like a pointer to an array of RGB LEDs. So like basically like values for RGBs. So these are going to be our LEDs. Then we're going to have let's make it a uint16, which will contain the number of LEDs. And then we need the specifics of the port and the pin that we're going to use for this. So the port number is a uint32, and the pin uint16t, the pin is a uint16. So this is effectively going to hold all the data for our kind of LED array. Okay, and now we have those types. Let's actually make some functions here. So we're going to have a function WS2812B. We're going to have a function that is going to write. So we're going to give it a pointer to a struct. So we're going to give it a pointer to our WS2812 struct. And that is just going to perform the full like write of all of the LED information. Like that is effectively our public interface. It's a really simple driver in that respect, and like probably you might think we want to add something for like init that would maybe do the configuration of the port and the pin. That's true. If you're following along with this, you can do all of your own API design. I'm going to leave it at the bare minimum. The bare minimum for this to still be a pretty effective driver. And yeah, I'm going to go off and implement this function now. So I'm going to go into the source file and add a WS2812. Am I adding a file here or not? WS2812b.c will include WS2812b.h. And before we forget, let's add it to the list of objects. So this is going to be WS2812b.object. So this is going to make sure that we generate an object file for this in the final binary. And what do we have? We have this function that we need to implement. And we know, for example, that we're going to need these ones as well. So let's come and grab those, and we'll just dump them in here. And of course, we don't have the idea of GPIO port, and we don't have LED port and all of that. So let's kind of fix that now. Let's include GPIO up here. And so that will give us these functions, but we need to now take in a pointer, not to the LED, not to this whole thing, but we actually need to take in the uint32t port and the uint16t pin, and then we can use port and pin for these. Okay, so now we have those timing functions bundled in here, and we can call them with the port and the pin. When we go to write, effectively what we need to do is we need to iterate through all of the LEDs, right? So we've potentially got some number of LEDs, right? We've got the number here. We need to iterate through every one of those and send the data for all of them. So let's do for uint16t I equals 0, I is less than WS2812b number of LEDs, I++. So we're going through all the LEDs, and what we're going to do is to send the red, green, and blue channels. So let's do that. Let's get our color. So this is going to be an RGB T, is going to be the LED, and that is WS2812. 12 LEDs at I. So we'll just sort of make a copy of that into our local environment here, and then we're going to say for uint8i is 0. We can't use I. This is going to have to be bit is 0. Bit is less than 8 because there are always 8 bits to send. Bit plus plus. What we're going to do is we are going to look at the right bit, and if it's a 1 then we'll call send 1, and if it's a 0 we'll call send 0. It's that simple actually. So in the sketch, in the protocol part, in the signaling, we can see that we need to send the most significant bit of the green channel first, then the next, then the next. So what we can do is just always look at this top bit and shift the bits up, and we'll do that 8 times, and then we'll always look at what this bit is to figure that out. So let's do that. So we'll say if led.g, because we're going to send the green channel first, ANDed with hex 80, which will look at the top bit. If that's a 1, then we will send a 1. And we will send a 1 to WS2812B port and WS2812B pin. And this is going to be sending the green channel. So that's green. Then we're going to send red. For that, we need to look at the right bit for that. And then we're going to send blue. Okay, so that is going to send that data, and then finally we need to wait 50 microseconds. And we need to actually count 50 microseconds. So this time I'm not going to insert the number of no-op instructions we need to get to 50,000 nanoseconds, because that's going to be a few too many for my liking. This is already quite a big function when you... oh, we should have Zen zeros in all of these as well. Yeah, so let's make sure we have that. Else... send 0, and then we should need to have that here and here. Okay, and at this point we're going to create that 50 microsecond pulse. So this is going to be the reset code. All right, so in order to do this, we're going to have a for loop, and we're going to run for some number of iterations. And the number of iterations, well, if we think that roughly 2 no-op instructions is 20 nanoseconds, then we need 50,000 divided by 20, which is like 2,500. So if I is less than 2,500, keep going, and we will just insert some. And you can see that we could figure this out in a slightly different way. We could trade off code size and number of loops and all that kind of thing. But we'll just stick in 2 nops at this point. And we'll see how close that gets us. And I'm curious to see how long this reset code ends up being in that respect. So let's try this out. Yeah. Let's go back to the firmware. Let's bring in our WS2812B header, and we'll give this a shot. Okay, so to do that, we need to add, or remove rather, some of this stuff. We can remove all of the send 0, send 1 stuff. And we can say that we would, well, I guess we need to make up a struct of WS2812B, and that's going to contain some LEDs. Yeah, I guess we should make the LEDs first, because then we can pass the pointer straight away. All of this would be useful to wrap into an actual API, and I may actually go and implement that, even though I mentioned that I wouldn't earlier. I may put that in anyway. So RGB_T, and we're going to make an array of LEDs. I guess at this point we can make all 8 LEDs. I have 8 LEDs on this. You can make this number as large as you want, but let's just make 8 in this case. And by default, we'll just set everything in that to 0. That makes some amount of sense. Identifier, RGBT is undefined. Did I just call that RGB? No. That's weird. Oh, I said RBG, yeah. Okay, so then we're going to set the LEDs equal to LEDs. We're going to set the number of LEDs equal to 8. We're going to set the pin to GPIO 8 and the port to GPIO C. Yeah, okay. So now we have that, and what we can do is to what we can do is to just, I'm just going to set the first LED up. So LED 0 dot, let's just set the blue channel to 255. And what I'm going to do is actually just run the function WS2812B write. I'm going to run that twice in a row. Or we'll just run it one after the other. So then we'll see how long that reset pulse is. So WS2812B underscore write. We will pass in a pointer to our thing, and then we're just going to immediately do that straight afterwards. And if I run this on the device, what we should see is the thing go blue. Wow, actually it's quite glitchy. So something weird's going on. So actually the first, probably you won't be able to see this in the with the light in here. The first LED is blue, but the rest of them are sort of glitching out, and I'm really curious about why that is. Maybe we're sending data too quickly, but what I want to do is to look at that on the Salier, on the logic analyzer, and see what kind of signal that that looks like. Okay, so that's all signal line, ground. Let's switch view to the Salier, and I'm going to just take a look there. Okay, so what we have here is this is going to be the green channel. Then we have the blue channel here where we send all ones, and then the red channel. And then for the rest of the LEDs, we're going to be sending all 0. So these are all zeros, and then eventually we're going to have here what appears to be a 208 microsecond pause, which is quite long actually. It's like 4 times longer than we need it to be. And I wonder how much of that is down to this, because we're just immediately writing, so we're going straight into doing this again. So yeah, let's just divide this by 4 roughly. So instead we'll do something like, I don't know, let's just do 600 iterations for now. Run that, take a little look if that sort of fares better. That gives us a 51 microsecond pulse in between, which should be perfect in fact. And, well no, of course the LEDs are not going to look good after that. But I am going to plug it back in now and see if we can get something out of it. And of course, if you're just setting the same value, Yeah, okay, so it seems to sort of glitch out the LEDs a bit. I'm getting the first value is correctly written. Oh, how can we take a look at this? So everything else just should be 0. I wonder, just to check something, if I put in kind of like a little delay here, so we don't immediately start running the next thing. Although, yeah, we should be able to push out at a 50 microsecond interval. Just check here. If if it's been 1 millisecond, which is quite a lot longer, then we will do this. And then we can just say start time is system.getTicks. Just want to see if kind of sending this once, and yeah, okay, that does actually calm the calm the situation down quite a bit. So if I show you on the camera now, I think you should be able to see that we just have one blue LED, and it looks pretty stable. But still, we shouldn't have to wait an entire millisecond in between. I do wonder if we were sending these out and all of the LEDs had a different value, or had at least a value that wasn't 0. Yeah, let's just try that quickly. For UN8T, I equals 0, while I is less than WS2812B number of LEDs. I plus plus, and then maybe we can just set them all to blue. This would actually be a good experiment just to check that this has worked. And maybe let's set 2 channels here. So let's set the red and the blue, so we should see a purple light. It's probably going to be pretty bright. Okay, that looks good. So there's a purple light. Without turning the lights down here, I don't think I've got quite enough range to be able to show you that here. I'm going to take this out again and see if we just sort of run it again and don't put any delay time in between. It actually seems also quite stable. It's not flickering, so that's a good sign. And also it is just purple, so it doesn't seem to introduce any artifacts from the green channel or anything, so I think that's probably okay. I wonder, probably we'd need to do something a little bit smarter than to try and sort of be able to set the LEDs completely off. Probably we need to write 0 to any LEDs that we don't want to show, and then on the next iteration just not write those LEDs at all, although you can't always predict that you wouldn't do that. So yeah, we need to see a little bit. Of course, you should not call WS2812 write more often than you need to, and of course we're calling it far more often than we need to right now. And since we're not updating the value, there probably is... I'm not exactly sure. I have the feeling it should work, so I'm not exactly sure whether it doesn't work. Okay, last thing to do here before we just clean up the API a bit is to perhaps just make sure that we can do this more dynamically. So I'm going to just make a small demo where we like run an LED kind of across the LEDs, or run a pattern across the LEDs to get a sense of that. So I think we'll do this every 250 milliseconds. We will kind of write the current state, and let's keep track of the UN8T current LED. And what we're going to do is to say that every 250 milliseconds we'll just write the state of the LEDs, or rather we'll take whatever the current LED is and that's just going to be in our LEDs array. Current LED, just going to set that to, I can just mem set it, I guess. And then we need to bring in the string, which we have. Going to set this structure to be 0, and the size of that is just the size of the RGB T. So that's gonna like clear out the entire thing there. Then we can take current LED, add 1, but in fact let's do it like this, equals current LED plus 1 mod the number of LEDs that we have, and then we will take the current LED and set its, I don't know, let's do it in green. Let's set its green to 255. So what that should do effectively is to just like move the LED across like by 1 every 250 milliseconds and then wrap back around. So let's try that. I'm going to run it. Yeah, it seems to look pretty good. I'm going to switch over. I think you're going to be able to see this because it's not too much. Yeah, that's seeming pretty good. And yeah, so let's actually just, as a last point, clean up the API. And by clean up the API, what I mean is, I think what we're going to want to do is to, because I think we can leave this part here, right? It's totally acceptable that we configure the GPIO without actually configuring, like without having to do that as part of the WS2812 driver, because that's what we need to do for anything else, right? If we need to have PWM on a particular pin, we configure the PWM without talking about the actual GPIO we connect it to. And I think we should think about the same kind of thing here, like that should be more on the configuration side at this point. But what I do want to set up is maybe a function called void WS2812B init, and we'll take in a WS2812B struct, a pointer to a struct, and we can also just take in yeah, I guess we could we could kind of construct all of this information there, or we could do it separately. We could even return this struct, right? Because it's not a large struct, so passing it around over the stack is also not really a huge problem. Now, maybe we don't even need this function actually, and we can leave it. Because kind of setting up the LEDs, it's not that much work, and it will probably cost us more to add in this extra call just to do the same thing that we could do here. So yeah, let's leave it like this. And in that case, I think we're kind of done. Yeah, I think we're kind of done with this. And let's just I'm just thinking, do we need to do anything else with it? I do want to revisit this in the future. It's not actually a complete mystery as to why I've chosen this device as something. I would like to build some more involved hardware in the future using these WS2812s. And one of the things in particular I'd like to do is to build like a persistence of vision display. This is something that I've been playing around with in the last couple of weeks, and I've been doing it with just regular LEDs, so just like a few regular LEDs controlled by an Arduino. But I think it would be pretty cool to actually build this whole thing, maybe put it on a board of its own, and actually write the firmware for a persistence of vision, like an RGB persistence of vision, and try and get like some resolution out of it. So maybe use 16 LEDs and kind of spin the whole thing around, try and get some text and some, maybe even some images, I don't know, depending on the level of complexity of that. But that's just one of the things I'd like to experiment with. And I would also like to experiment with doing some more kind of driver level videos. So exploring, like grabbing a device, writing a driver for it, seeing where we can get with it. I think that's kind of quite fun, a fun way to explore, and probably quite a communicative way for you to also get on board and explore these kind of things, because I think a lot of people they are able to get started with something like an Arduino or even with an STM32, but then kind of when you start to think about, like, well, how can I really put a system together, or how can I write the code and drive some of these things, it starts to become more complex, and actually it doesn't have to be. We just need to be able to break things down and design them in the right way. So that's just something I'm thinking for the future. Let me know in the comments what you would be interested in seeing in terms of devices and things like that. I wish you the best of years next year. If you're watching this in the future, of course, disregard all of this, but like, Happy New Year, and I'll see you in 2024.